Okay, so for our next problem, we have this box that's like hanging off of, there's a rod. So we have tension in this rope and then this rod and then a weight kind of hanging down. So we want to know the tension of the rope and then the force exerted by the pivot on the beam. So the magnitude and direction. So what that means, okay, so step one, we're told that we have a pivot. When we looked at our table in the beginning for this section, we found that a pivot is modeled like this, right? Where we have two pinning forces. This horizontal and vertical force, you can call them whatever you want. You can call them like XFY, FPX, FPY, up to you for the naming convention. In this case, they just call them V for vertical and H for horizontal. Those forces would exist here. So this is the horizontal, and then we have a vertical force, right? V for vertical. The reason why they're there is because this horizontal force is they're pinning. So the beam can't move into the wall and it can't shift up, basically. So it can't move up and down and it can't move back into the wall. Okay. When they ask for the magnitude and direction, if we think of these as like x and y components of like a vector, like h in the x hat, y in the y hat, and we want to find the magnitude of a vector, this is how we would find the magnitude of a resultant vector. And then this would be how we would find the angle of a resultant vector. So this is just sort of a throwback to week one. So when they said the magnitude and direction, they want to know the net magnitude and direction of the total force acting on this pivot point here. Okay, so so we talked about how to model this pivot. We also have just like a tension force kind of coming out of here. So the tension force is just going to be internal to the rope. It's going to be pulling right on both sides. But the way that we model these is we want to take the object that has mass that's going to be rotating and we're going to separate it right from everything else. Just imagine drawing like a dotted line and we're going to separate it and we're just going to look at the forces acting on that thing that would experience the torque. Okay, so the object with mass under equilibrium that everything's pulling on. So we're going to separate it. We're going to pull it out as like a chunk, and then we're going to model all of the forces on it. Okay, so that's kind of what's going on down here, right? So we see the H and the V forces. So these are moved so that this is kind of the better convention to draw them. These are moved so that the base of the force is acting at the center of the pivot point. Okay. Then this force that you see here is actually just the weight of the bar. So the weight of the bar is going to act at the center from coming down from the center of mass. And then the weight that you see here is the weight of this box. Okay, so that's just the weight of this box. So we were given the masses. So this is 100 kilograms times gravity. This is 25 kilograms times gravity. Okay, so far so good. All right. Now, because we have a statics problem, what we want to do is we know that the sum of forces in the x is equal to 0, sum of forces in the y is equal to 0, and the sum of torques is equal to 0. And we know that because the system's in balance. So there may be forces on the system, but because it's not moving, because there's no motion, everything's balanced. So we're going to use that balanced property to solve for our unknowns. Okay, let's talk about how we're going to do that. So first, let's look at how to find our x and y component forces. So it's going to be a little tricky for this tension, right? Because we have this h that's in the x direction, but this tension is kind of up at a 50-degree angle, and this 50-degree angle is like kind of at an angle from the horizontal here. So if I want to figure out exactly what angle it is from the horizontal, which is where I'm measuring, taking my x from, I kind of have to do a little bit of like trig or geometry gymnastics a little bit here. So that's a 90-degree angle. So this would be a 20-degree angle, right? 20 degrees, because I know that my triangle, right, is 180 degrees total. And that means that, so 70, so I have a 90-degree angle and then 70, right, plus 90, right, minus 180 equals 20, right? Because I need these two other angles to add up to 90, basically is what I'm saying. So that maybe that's a little bit too much of an explanation, but I need these other two to add up to 90 because I need my triangle, the sum of my angles for my triangle to be 180 degrees, right? Triangle, 80 degrees. Okay, so Again, some fun geometry throwbacks. Okay, so now that I have that angle, I'm going to break up my tension force, right? That's my 30-degree angle. I want my TX and I want my TY, so I can add it to the X and Y components, right? So my TX is going to be T cosine of 30 degrees. So this side right here, that's going to be, so I'm going to have T cosine of 30 degrees. And it's actually going to be a negative because if this is my positive X, positive Y, it's going to be pointing this way. So it's negative. All right, then I also have this positive H, right? That's also pointing in the x-axis, this guy right here, that positive H down there. And that's everything for my X, right? That's everything. I have the, right, TX, TX and TY. Okay, cool. All right, now let's look at everything in the Y direction. Okay, so in the Y direction, I have, let's look at what's positive first. So I have V acting in the positive. Then I also have TY acting in the positive. So that would be T sine of 30 degrees, right? It's across from this angle right here, T sine of 30 degrees. Then I have minus 245 newtons, right? Just going straight down, minus 980 newtons. And that's all equal to 0. Okay, so now I notice that I have two expressions. So what am I trying to find in this case, right? I'm trying to find my H and my V, but I don't know that tension. So I still need to find the tension. So I'm going to use, I have two equations, two unknowns, or three equations, two unknowns. So let's get another equation. We're going to use the torque equation to find the last pieces here. Okay, so let's look at the torque from the weight of the beam. So the torque from the weight of the beam, or let's find all the pieces. So sorry, before I say that. So when we find the sum of torques, we pick a pivot point. Pivot point can be anywhere on our object, right? That's in equilibrium. So this object is the one that's in equilibrium. We're going to pick a pivot point. We want to pick a pivot point that has unknown forces on it, because if this is our equation for torque, the r distance is the distance that the force is away from the pivot point. So if we pick a point with unknown forces, they're going to be at r equals 0, so they're going to drop out of our equation. So if I pick this pivot point here, I'm going to have these forces and then tension basically acting. And so then I can just solve for tension. And that lets me get my tension, and then I can use the tension here and here to get H and B. So that's what I'm going to do. Okay, so taking it at the pivot point with the most unknown forces, I'm going to start. So I just have 0 for my first torque, right? So for torque for V and torque for H, 0, right? For this first one. Okay, and then what else is going on? Now I have the weight going down. Okay, so RF sine of theta. Okay, so what is my R distance? My R distance is the distance from here to here. And this is my theta, the angle between the force and the lever arm that is working. So we're halfway, right? So this would be 1 meter. And then my angle here, well, what would that angle be? So again, with some geometry tricks here, let's think about this. So if I say this line is parallel to this line, right, because they're just both going straight up and down, I can say that this is just some line that's bisecting two parallel lines, and I can say this angle is equal to this angle, 70 degrees, right? Okay, and then I can get that angle there. So I have 70 degrees. So this would be the weight, and then the distance is 1 meter, right? So we said 1 meter, right? So 1 meter from here to here, and our force, negative 245, minus negative 245. And then what was our angle? Sine of 70 degrees. Okay, cool. So that's the torque for the, I'll put it up there, torque for the weight. Okay. All right, next we're going to do the torque for so the weight of the bar. This weight of the bar. Then we're going to do the torque for the box. Okay, and that one is the full length of the rod. So the full length of the rod is 2 meters. 2 meters. So 2 meters for that whole length of the rod. The angle is also 70 degrees, and then the force is 980 newtons. So negative 980 newtons. 180 newtons, and then sine of 70 degrees. Cool. Okay. Now, last one is our tension. We have to use our tension as well. So I'm going to make this all a little bit smaller so we can fit the tension in also. So I did, right, these two, which were 0, the tension of the weight of the bar, or the torque from the weight of the bar, not tension, torque from the weight of the bar. And then I'm also going to add the torque from the tension. Okay, so the torque from the tension, so it's going to be acting 2 meters. This is a lever arm, right? 2 meters for the tension. And then the net angle of between the tension and the lever arm is 50 degrees, right? So it's going to be T times 2 meters, right? Because that's the length of the bar. And then it's going to be sine of 50 degrees. 50 degrees. Okay, cool. So now I just have my only unknown in this equation is tension. That's the only thing I don't know. So I can just go ahead and solve for it. So I'm going to have tension, right, is going to be equal to negative 1841.8 Newton meters. Oh, I'm sorry, that's not correct. That's the net torque. Sorry, I'm looking at the wrong thing on this sheet. I apologize. That doesn't make any sense. Okay, the tension, if I just plug all this into a calculator, is equal to 1352.4 newtons. Sorry, I was pausing for a second there because I'm like, those are not the correct units. Newton meters is for torque, not tension is a force. Tension is a force, and so the units would be newtons. So if that didn't raise a red flag for you right away, just sort of think twice about that one. Okay, cool. So we found our tension. Now that we have the tension, we can use sum of forces in the x and sum of forces in the y. We know that that's equal to 0, and that's equal, so we have negative t cosine of 30 degrees, right? Just say t cosine of 30 degrees is equal to h. So I'm just taking it from up here, right? Setting them equal to each other. And then some forces in the y. I can do the same thing here. I can have V is equal to 245 newtons plus 980 newtons, right? Just moving that over, minus T sine of 30 degrees. Okay, so just moving these things over to the left because t equals 0. And then I'm going to solve for those guys. So then I'm going to get, it's very annoying, sorry, H is equal to and V is equal to. So H is going to be, H is equal to 1171.2 newtons. And then V is going to be equal to 548.8 newtons. Okay, so far so good. All right, so now that I found the tension and both of those, what I'm going to do is what we talked about. So now that I have these guys, I need to find the magnitude and direction of my pivot force, or the force exerted by the pivot on the beam. So this is the pivot. It's called a pivot. And I want to figure out the total force that's being exerted by that pivot. So I'm going to use this equation here, plug in my, my values for v squared and h squared, and I'm going to end up with r is equal to the square root of both of those. And if I plug those guys in, it's going to be, this is just the resultant. R means like resultant force. So 1293.4 newtons. So that's my resulting force. And then my theta is going to be equal to 25.1 degrees. Okay, so that means that the resulting force kind of here down at the bottom, if I have this, this beam, the force to kind of keep this all in equilibrium is going to be kind of up this way. So 1293.4 newtons, and then the angle that it makes with the horizontal here is going to be about this 25.1 degrees. Okay, so yeah, then this would be, you have like your weight and the tension and whatnot going up. Okay, so that's that would be your final answer for this. in this case.